So in question 12, we're given this function f of x, and in part A, we need to use induction to prove that the nth derivative is equal to this expression for 8 marks. So whenever we have an induction, usually the first couple steps are 3 marks. Anyone can do that. So the first step is always to show true for n equals 1. Or like for the first one here, we are told that n is a positive integer. So the first case is when n equals to 1. So we need to find the first derivative of f of x. So let's find the derivative of this. So we can firstly use the power rule. This would be minus a half times 1 minus ax to the power of minus 3 over 2. And then the derivative of the inside function is minus a. And then what we see is that we can plug in 1 into this formula as well. So that would be a to the 1, so 1a. And then 2 minus 1 factorial is just 1. And then we have 1 minus ax to the power of, well, minus 3 over 2. And it's all divided by 2. So indeed, we see that these two are equal, so it is true for n equals 1. Second step, we need to show true for, assume true for n equals k. Or n equals k. So let's write down the kth derivative. We assume is given by this expression. Like this, all over 2k plus 2k so 2k minus 1 times k minus 1 factorial, and on the top we still have 1 minus ax to the power of minus 2k plus 1 over 2. So in the first step we need to show true for n is equal to k plus 1. So what this will look like is we have to plug in k plus 1. So the k plus 1th derivative x is equal to, well, then we just rewrite the same thing but with k plus 1. So this will be 2k plus 1 factorial times 1 minus ax and a minus 2k plus 3 over 2 divided by 2 to the 2, oops, 2 to the 2k plus 1 times k factorial. Alright, and now the work begins. Until now, this was just pretty much kind of robotic. Anyone can kind of do this for a couple marks. But now the real work begins because we need to show that this is actually true. So how do we do that? What we usually need to do with these derivatives is that we need to take the derivative of the kth derivative, as that will be the k plus 1th derivative. And if we take the derivative of this and we get this, then we have shown that it works. So then we have proven our statement. So I think what I will do is make a little bit more space, delete the first step, and copy all of this a little bit up, like this. And then we can write down what we need to do. So we need to find the derivative. So the k plus 1th derivative at x is equal to the derivative of the kth derivative. So we have to just take the derivative of this. All right. So let's do that. Firstly, what I would want to do is kind of take out all of the constants here. So anything that doesn't have an x, we call a constant. So like this term, this term, this term, this term, they're all constants, so we don't need to take the derivative of those. Those can just be simply pulled out. Assume true. All right. So let's pull those out. So f of k plus 1 in the place of x will be equal to a to the k times 2k minus 1 factorial divided by 2 to the 2k minus 1 times k minus 1 factorial. And then what we need to take is the derivative of this expression over here. So we can simply use the chain rule and the power rule. So we need to take down the power. So this will be minus 2k plus 1 over 2. We multiply it with the original thing to the power of, well, we need to subtract 1 from this. So that will be minus 2k plus 3 over 2, and then times by a minus a because of the inside function. So we already see that we have some similar terms with the exponent of 2k plus 3, so that is nice to see. But we need to do a lot of simplification here to kind of get it to look like this term over here. So this is our goal. So we want this and this to look the same. Then we have proven our statement. So let's continue. So what we can do here is, well, firstly, we can kind of write down the start as the same. Like this. Like this. And then here, we can simply multiply everything out and just take this minus a into consideration as well, so that we have a couple less terms. So this will simply be a times 2k plus 1 over 2 times 1 minus ax to the power of minus 2k plus 3 over 2. So the negatives have cancelled each other out. And then the next thing we can do is, well, yeah, so we can, this brackets here isn't really necessary anymore. We can multiply out this bracket, as this is just the sum of a bunch of terms, so we don't even really need the brackets here. So what we can write here is, a to the k plus 1, as we have this a to the k and this a over here, and then this will be multiplied with 2k minus 1 factorial divided by 2 to the 2k. Again, we can combine this with this 2, and is multiplied with k minus 1 factorial, and then there's still a 2k plus 1 and a 1 minus ax to the power of minus 2k plus 3 over 2. All right. So now we need to look back at what we want to achieve, right? So what we need, we kind of already have this a to the k plus 1. We almost have this 2 to the 2k plus 1. But what we well, this we also have. But what we wanted is 2k plus 1 factorial and this k plus 1 k factorial. So we don't really have these yet. So what we can notice is that we can rewrite these terms over here. So these terms we don't really need. We kind of want to transform them into some shape or form into that. So we can say that k minus 1 factorial is simply the same as k factorial divided by k, because k factorial is just k times k minus 1 times k minus 2 factorial. So that's just the same as k times k minus 1 factorial over k, and that will just be k minus 1 factorial. And the same with 2k plus 1, we can write 2k plus 1 factorial over 2k factorial. Again, same thing. This will be 2k plus 1 factorial, 2k plus 1 times 2k factorial. 2k factorials cancel out, and so we're just left with the 2k plus 1. So I'll scroll down a little bit here so that we have a bit more space. All right. So what we can do next is kind of write these new terms back into here. So this will be like a fraction inside of a fraction, and this, so we can take the reciprocal of this to make it a little bit easier for us, and then yeah, we can continue working with that. So what we will have is this is equal to a to the k plus 1 times, well, the k can come up as we said, so we'll have the same 2k minus 1 factorial times the k from over here, and then we will still have the 2k plus 1 factorial. We will have the 1 minus ax to the minus 2k plus 3 over 2, and this is all over 2 to the 2k times 2k factorial times k factorial. So now we're getting somewhere because we have the terms that we have wanted. At least we wanted this term to be here for sure. So we're at least getting somewhat closer. So what we can see now is that this here can be simplified. So 2k minus 1 factorial is just like saying, so 2k factorial is just 2k times 2k minus 1 factorial. So this can be removed from here, and this will just become a 1. I mean a 2k. So let's rewrite that. So we have a to the 2k plus 1. So that from the top it will just get removed. So we have a times k times 2k plus 1 factorial times 1 minus ax minus 2k plus 3 over 2. And then we have a 2 to the 2k times 2k times k factorial. All right. So again, we can notice that we have this 2 to the 2k multiplied with this 2. So this can be simplified to 2 to the 2k plus 1. And we also have a k on the top and on the bottom, so these will cancel out. And so this is equal to a to the k plus 1 times 2k plus 1 factorial times 1 minus ax to the power of minus 2k plus 3 over 2, and all divided by 2 to the 2k plus 1 times k factorial. And now, if we look back, this is indeed, if I would have not forgotten a 2 from here, so if we compare this to f to the k plus 1, this is indeed the same. I just forgot a 2 from here. But so we have a to the k plus 1, this is the same, this is the same. So everything is the same. So we have finally shown that that they're indeed the same. So what we can do now is write our final statement for what we need to write for mathematical induction. So we have shown true for n equals 1. We assumed true for n equals k and have proved it true for n equals k plus 1. Hence, by mathematical induction, the statement is correct for, and then we can look back at the question. So it is true for n element of the positive integers. So this is how you show this through mathematical induction.